Today, I'm going to show you how to design the control loops for the average current mode control of the buck converter using the AC sweep function of the PSIM software. So now, the main idea here is that we start from the PSIM schematic. So I have already a PSIM simulation, and the first step, I will do the AC sweep function from the PSIM in order to get the current plant. After that, I want to export the frequency response to SmartCtrl in order to design the control loop, the inner control loop of the average current mode control. After that, I copy the parameters and simulate in PSIM software, and I will check how is the converter response. After that, we also repeat the procedure to the other loop in order to control the output voltage. So in this example, I have this PSIM schematic. This is a typical buck converter. This is, now is in open loop. The first step that I have to do is I have to insert a perturbation. So I want to select the AC sweep element. Also, I have to inject a perturbation in the duty cycle. So here, I put here. This is the duty cycle in a operating point. So now I have to select a sine source, and here is the name is V2. So now in the AC sweep function, I set the amplitude in 0.1, like it's maybe 5–10% of the operating point of the duty cycle. And this is the switching frequency of this simulation is around 100 kilohertz. So now I set close to the half of the switching frequency, maybe 40 kilohertz, from 100 hertz to 40 kilohertz. And now I have to select have to put the AC sweep proof. So AC sweep proof in the inductance current. So now, okay, I have to change the name of the, here is V2. So now we have to wait some, I think it's last 1 minute the simulation, in order to get the frequency response of the inductance current plant. So in SmartCtrl, when I open the software, this is the initial dialog. So here I have to go to this option, to design generate topology, select the option import frequency response data from a TXT file. So if I select this option here, I have to specify if the control loop is in voltage mode or current mode. In this case, for the inner loop, we have to select the current mode control. So we have to click on OK. And now here, I have to define what is the current at the operating point. In this case, is like 60 ampere. And here we have to define the switching frequency. In this case, it's 100 kilohertz. So we have to wait a little bit. Or I already have the TXT file here. So in this case, this is the current plan. So I have to open and click on OK. After that, we have to select the sensor stage of the control structure. In this case, I select a current sensor. and here we have to define the gain. In this case, I select the unity feedback gain. So click on OK. And now it's time to define to select what is the compensator that I want to tune. In this case, for example, I select a PI compensator. Here, these parameters are related to the modulator. So here we have to define, in order to get a unity gain of the modulator, we have to define here the peak value equal to 1, the value to 0, and the rise times, we have to define the 10 microseconds. So click on OK. Then we have to select one point in the solution map in the white area that ensure that the control will be stable. So for example, I select close to the 10 kilohertz and 50 degree of the phase margin. So click on OK. And then we have to click on OK. So this is the okay. This is the control loop that I already tuned. So here we have the PSIM simulation finished. So is finished. Now this is the same txt file that I uploaded in the SmartCtrl. So here, next we have to copy the parameters of the PI compensator. So the key P and the TI. So now, in this case, I have to remove this part, the perturbation. I have to select a PI compensator. Here we have to define some limits. So the lower limit, for example, is 0, and the upper limit is I choose 1, for example, because the duty cycle, the peak value is 1, and the valley value is from the carrier signal is 0. So this is our limit, and here we have to copy the value of the key pin. So millis, and this one, the TI, is microseconds. So now we have to calculate the error. So here we have, this is the sensed current, and we have to select one reference. In this case, is 60 amperes. So I disable the AC sweep block, and now I simulate this converter. So now we want to select that the inductance current is achieve the reference. So also you can see how the dynamic response of the control is similar that is predicted in the SmartCtrl software. So now it's time to define to tune the control loop for the output voltage. So in this case, we have to get the frequency response of the output voltage plan. In this case, we have again to inject the perturbation now in the current reference here. Maybe I want to show you this value we have here. And now we have to put the AC proof to the output voltage, sensed output voltage here. And now I enable again the AC sweep element, and here I change a little bit the amplitude of the perturbation. In this example, I set 2, for example. So again, I have to run the simulation. In the same way, now I have to close, for example, this design, or go to File, New. I access to this option, to the import from frequency from the import from the txt file if you go into this icon. So now, again, we have to define that our control now is in voltage mode control. Click on OK. Here we have to define the output voltage. In this case, is around 60 voltage, the switching frequency, and we have to select the txt file. In this case, this is the converter plant for the output voltage. So click on Open. Now I have to click on OK. I have to define the sensor stage. In this case, I select the voltage divider and I select a gain of unity feedback gain. So I have to change the value to this. So this is close to the unity. Click on OK. Again, we have to define, for example, a PI compensator. In order to get in this converter plant, we don't have to consider the modulator gain because it's already considered in the AC sweep transfer function. So here we have to define the peak value, the value is 0, and the rest time, click on 10 microseconds. So click on OK. And now we have to select a 1 point in the solution maps. So now, for example, I select 1 kilohertz of the crossover frequency and phase margin of 100 degree, for example. So click on OK, click on OK. And again, I have to copy the values of the parameters of the PI compensator, so the key P and the TI. So here is the simulation is running in order to get the AC function. Maybe I want to change this, so I have to remove the perturbation. I have to select another PI. In this case, I have to change the parameters. So it's 265 millis, and this one is 0.0 microseconds. So here we have to define another the limits of the limits of the PI compensator in order to make the anti-wind up. So here the lower limit is 0, and here, for example, is 100 amperes. And now we have to calculate the error here. So in this case is output voltage, and this is the reference. This is the AC sweep from the output voltage plan that I uploaded in the SmartCtrl, so it's correct. And now I will check if the control loop is stable. So now you can see this is the current, and the output voltage achieved the voltage reference, 60 voltage. Also, I want to show you that the duty cycle, the output voltage of the PI compensator is not saturated in this example. And this is the carrier signal of the converter. So the last step, if you want to validate if your control loops has the crossover frequency and phase margin that you select in SmartCtrl, you can also do the AC-sweep function for the open loop transfer function. In this case, I have to inject the perturbation. I have to inject the perturbation in the output voltage sensor here. And I have to select the proof, the loop, the AC loop proof. Go to the others, proof, AC sweep proof loop here. And to have to put here, in this case, and this is the T. So maybe in order to reduce the simulation time, maybe I put, for example, 500 Hertz. Okay, now the simulation is running. And here we can check if the crossover frequency is correct. So we have to wait some seconds. This transfer function is this one, the pink trace. So this is the open loop transfer function that I will to get from the ACSIM function from the PSIM simulation. So, okay, so this is the amplitude, and this is the phase of the transfer function. So here we can, maybe I want to export this information. So save as, and here go to webinar, here, for example, PSIM. Okay, saved. And now in SmartCtrl, if I go to file, I can import this txt file. So import merge. Here, I click on add the T function, txt file. And here, this is that I saved. So click on open. Maybe I want to change the color, maybe blue. Click on OK, OK, apply. So here you can see how the crossover frequency and the phase margin, it's already predicted by the SmartCtrl. So this is all for today, and thank you. This is the information. If you have any doubt, don't hesitate to write an email on this to this mail. Or also, if you want to get more information, you can go to the website, the Power SmartCtrl website. Thank you.